everybody, it's MoNaCo here.
And Milks.
We are in almost done. Unit 12, pages 10 and 11. We're going to do some transmutations.
Yeah, basically we're going to do those equations, make one side equal the other, and we all done.
Interesting enough, transmutation was like the origin of chemistry. Alchemy, back in the day, they were trying to transmute
lead into
gold to make money. We can do it now, but it's way too expensive.
Yeah, I'm not convinced we can actually do it, but.
Hey. So the law of conservation of mass governs all natural radioactive transmutations.
Okay. And the parent nuclei is going to be the starting unstable atom that decays into the smaller atom. So in this picture, it's on the left.
Yep. And the daughter nuclei is what it turns into. That's it.
There you go. So put some terms you need to know.
Parent nuclei, daughter nuclei. What was before, what was after the transmutation.
Okay.
So,
4 major types of transmutations we're going to study. First one being alpha. So the alpha particle is produced. There will be 1 reactant and 2 products. The daughter atom is, of course, going to be lighter. And we highlighted alpha particle on your reference table O. So that HE with the 4 and the 2, or the alpha symbol with the 4 and the 2, is what you're looking for in your equation. If you see that in your equation, like that is in our example equation here, now you know it's alpha decay.
Always write the particle that is the emission particle first, and then the second daughter. So
yeah, that's how I do it, because it just makes the math easier.
In this scenario, the mass of radium-222 has got to equal the mass of a helium plus a radon. And that's how the conservation of mass works. The conservation of charge, there's 88 protons, 88 positive charges in the radium nuclei. And the 2 daughters that are created after the split, one of them has 2 positive charges, and the other has the 86.
Yeah, so I noticed a lot of the practice that we had to do was like, all right, listen, you got radium-222 with an 88, and it's going to alpha decay. What's the product? And then, so you can go ahead and write the radium, put in your alpha particle, and then you're like, whoa, 88 minus 2 is, bam, boom. 86.
Yeah.
222 minus 4 is,
bam,
boom, 218. And then you go to your periodic table, look up 86, who dat?
Radon.
Radon. And then that's how we do that.
Yeah. So beta decay is going to be the same thing, but with a different emission particle.
Correct.
And there it is.
So that's your electron.
And these are typically lighter elements that you see beta decay, but not always. And the way it works is the same. A carbon-14 nucleus becomes a nitrogen-14 nucleus and a beta particle. You'll notice the atomic numbers are actually increasing in this scenario because the charge on an electron is a -1.
Right, so now I do a 7 for the nitrogen minus 1 for the electron, gives me 6 on the carbon.
So they're balanced.
It does still work.
There's that pesky -1 charge for electron that people can't seem to get.
Yeah, and then positron is actually kind of the opposite, because that's a positive electron.
Yeah.
So again, the mass is going to stay the same, but that number of protons now is going to go down and not up, because here I got a +1 plus 18 equals the 19.
Yeah. So we're just doing simple algebra, working backwards.
Yeah. I don't even know that it's algebra, to be honest with you. It's really
well, we're finding the missing particle. It's an X.
Oh, okay.
You know, if you really want to think about it.
Yeah.
Neutron capture, a neutron is a reactant, so this is primarily an fission reaction. You'll see the neutron capture, and there we have a fission reaction. Uranium-238, you add a neutron to it, becomes uranium-239, and some radioactive gamma emissions are produced as well.
Right.
And then all of a sudden that sucker falls apart into other daughter nuclei, making a whole cascade of different elements that we're not getting into.
Right. This is just that step. This is the neutron capture. And you see the neutron is in our reference table O, so we got to know how to use it. Again, all sides add up, so we good.
Yep.
And we just got some quick
examples.
Examples.
Let me grab the marker, you do the narrate.
Sure. All right, dig it. All right, so I see 88 on the RA, and I got a -1 on the other side. So what -1 is 88? 89. 226 minus 0 is 226. Look up on my handy-dandy reference table who 89 is. It's going to be right next to RA, by the way. AC, and there we go. It's that simple. In this case, I see an 84 going to an 82. What I lose? I lost a 2. And 209 going to 204, I lost a 4. 24, I can tell that's HE.
That's for an alpha particle.
Alpha particle.
Same thing. They're synonymous.
Right. They really are. Again, doing the math, I got a 92 for uranium. It's going to go to a 90. The 238 is going to go to a 234. Notice he's picking up the pace, looking up 90. Isn't that TH?
Thorium.
There you go. And there's a now I'm to 90 TH with a 91. Ooh, if I'm going from 90 to 91, I got to have a negative one on the other side. Instantly, it tells me beta particle.
Yep. Interestingly, here, this 238 uranium becoming the thorium then becomes something else. This is called a nuclear cascade.
Yes.
Which you've seen maybe in earth science, where you figure out where the nitrogen or the carbon-14 came from other places. But we don't get into that in chemistry.
Right. So I'm gonna on this last one, I'm gonna add up the right-hand side. I see I got to get to 9. So 7 plus what gets me to 9? That'd be a 2. Then I got an 18 up top. 4 plus what gets me to 18? 4, 2. Oh, alpha.
This is when nitrogen in the atmosphere somehow accepts a helium particle, becomes oxygen and hydrogen. It's what is a decay or transmutations all about. These elements are literally changing identities. Okay?
Right, now we got another practice page of these things, which is more of the same that we just did.
Which, I don't know, do we want to do all these examples? Because it's pretty basic.
It really is pretty basic. Why don't you just pick one so we can say we did something on this page?
Okay, we'll do number 6.
Number 6.
Add a helium nuclei to bismuth.
All right, so 83 and 2 is 85. Minus 0 is still 85. I got 209 plus 4. 213. 213 minus 1 is 212. Handy dandy reference table. 85 is AT, and that's it. So I know that there was a lot of talking our way through this, so I hope you were listening and not bumping. You guys need to finish this page.
And it's all about conservation of mass and charge.
Right side's got to equal, left side's got to equal. Oh, and since we spoke of charge, let's talk about that.
Yeah.
Charge in this case in nuclear chemistry is referring to nuclear charge.
Nuclear charge,
so,
not ionic charge.
Right, so now we're talking protons.
And maybe the electron that the nucleus emits is a beta particle.
Right, so that's it.
See ya.